So that book is the problem book for this. You have the physical book for this, no? Claydon.
Yeah, I do.
This is that South Asia edition, second edition, right?
1 second.
Second
Yeah,
edition.
yeah, second edition.
It is colored and all, no?
Yeah.
Okay, okay. Okay, fine. So that is the same book that I also have. So what we'll be doing here is we will be doing the theory from the book and then problems from the PDF that I've sent, right? So that will
Okay.
be a problem book for the same textbook. So in this, there are actually like quite a lot of chapters, 43 chapters. You don't need to do all of them, but we will have to do a substantial number. So right now, what we will start off with is chapter 1, chapter 2, and hopefully we'll also look at a little bit of chapter 4. Uh, chapter 3 is not something that we will do right now. Chapter 3 is spectroscopy, that is not in the syllabus. So basically, structures of molecules, if you want to find, there are some experimental methods by which we find those structures, right? So
Yeah.
it's not like you can see the atoms directly, right?
Yeah.
You will be able to detect the atoms and their special signatures using some spectroscopic experiments. So spectroscopy basically means the way you have learned in atomic structure, right? That certain transitions are allowed, right? So if you give some energy, an excited sodium atom, for example, will emit some particular wavelength of light when it comes back to the ground state, right?
Yes.
So suppose your sodium atom is excited, it is in the star state. Star state means it has more energy, right? So
Yeah.
what happens is basically that there is a nucleus. Let's say we are drawing the 3s orbital, right? Normally there should be one electron in the 3s orbital. It should be 3s1, right?
Yes.
However, it could be that when you gave it some more energy and it went to excited state, this electron was occupying some of the 3p orbitals, right?
Yeah.
It could be in 3p, which was empty, supposed to be empty. The electron was there actually, right?
Yeah.
So if it was there, and if this Na plus will later revert to the normal Na structure, then that means the electron will come down from 3p energy to the 3s energy, right? So
Yes.
3s will have lower energy level than 3p orbital because of the n plus l rule, right?
Yeah.
N plus l rule is the rule for deciding the energies of the orbitals, right?
Yeah.
So in 3s, it is going to be 3 plus 0, and in 3p, it is going to be 3 plus 1, right?
Yeah.
This energy is more, this energy is less. So obviously, it will lose some energy and come back down to the 3s1 level, right?
Yeah.
The energy that it loses, the gap in energy, right? Change in energy, right? Is converted to a wavelength of light, right?
Yeah.
So this wavelength will be determined by the actual gap in energy, right? Actual gap in 3s1 and 3p1 for sodium, right?
Yeah.
For sodium, the actual gap in 3s1, 3p1 will be somewhat similar to this. If you remember, this is something like this is the energy 13.6 z square by n square ev. This is in electron volt. This is for a Bohr model hydrogen atom, okay?
Yeah.
Right. But
Yeah.
actually, this formula is not accurate for sodium and all. But I am saying approximately this is the type of formula it should be, right?
Yeah.
So clearly, the energy depends on the Z, right? Atomic number.
Yes.
So for sodium, the Z will be different. For lithium, it will be different. For other things, it will be different, right? But
Yes.
n is the principal quantum number, right? So the gap between 3s1 and 3p1 will be unique for sodium. 3s1 to 3p1 gap for potassium, for example, will be different, right?
I don't know.
Why? Because Z is different, no?
Okay. Yeah.
It depends, the energy depends on the atomic number and the principal quantum number.
Yeah. Yeah. Yeah.
So obviously for each element has a different atomic number.
Yes.
So all the transitions, all the energy differences will be different values for different elements, right?
Yeah.
So since all the energy differences have different values, therefore, for sodium, when the light comes out, when it comes back to its normal state, the wavelength of light is going to be unique for sodium, right?
Yeah.
So what people did is they did many experiments on many different compounds, and they found many different wavelengths that were coming out, right? And they built a table, or they built a table with information containing when hydrogen comes back to its ground state from say 1 2s1 level, right? It emits a line of frequency this or wavelength this, right?
Yeah.
So after a lot of experimentation, you will now be able to figure out, given the spectroscopic data means excite the atoms, then measure the light that is coming out, right? Then see the light that is coming out and measure the wavelength of that. Okay. So such data, when you see the wavelengths, what you will be able to say from there is that, oh wait, this was hydrogen because this particular wavelength only comes from hydrogen, right?
Got it. Yeah.
So people figured out ways to derive the structure of an unknown compound by looking at this spectroscopic data, right? And that is what chapter 3 is going to focus on. Chapter 3 is there are different types of spectroscopy. That's the field in itself. NMR spectroscopy, infrared spectroscopy. There is a whole experimental science through which people look at an unknown compound and they're able to say, wait, this compound has one oxygen, two carbons, and something, right? And one nitrogen. Okay. So that is not in syllabus. That will be important only when you do chemistry at a later stage. So for now, we'll not be going into details of it, but you have to realize that all of the chemistry that people have figured out or learned is based upon, like, the structures that you are drawing is based upon actual experiments with infrared spectroscopy or NMR spectroscopy, which figured out that, wait, this unknown compound had 3 oxygens and 1 nitrogen and whatever, right?
Okay.
Because you cannot actually see the atoms, they're too small, right? They're
Right.
too small and you cannot actually see them. You can only do an indirect experiment like this, and it's almost like doing some detective work. You have some unknown thing and you have to figure out what it is. You cannot directly see it, and you have some tools, right? Spectroscopy is one of those tools. So chapter 3 is not something that we'll be doing. We will be assuming that the structures are the same and the formulas are given and we know what is there in each compound. But right now, we'll just begin with chapter 1 and hopefully start at least chapter 4. So chapter 1 is very basic. Chapter 1 is just talking about introduction to organic compounds. Okay. So he's talking about organic compounds. Earlier, people thought that organic compounds were only compounds that were existing in biological systems. So biological systems, as in living things and all. So they thought that it has something to do with life and all. And people thought that you will not be able to synthesize these organic compounds, but that is not the case. What happens is it is ubiquitous in nature; it's everywhere, and the definition of organic chemistry is basically the chemistry of carbon compounds, and we will be studying those carbon compounds only. And let's just keep going ahead. Here, organic compounds, he's talking about how many there are so many, 16 million uh, different organic compounds are known right now. 16 million. So, and there might be many more which we have not yet counted. So it's quite a big subject, and it's very important because lots of industries are driven by all of this. So anyway, these parts are not so important. He's describing some interesting examples and all. You can just read it for just curiosity. Organic chemistry and industry, that is also, see, there is a table here which says these are the ingredients, this is the chemical meaning, and these are the purposes, these are the uses to which they have been put. So if you see detergent, there is a huge organic compound there, right?
Yeah.
So C12H25 and OCH2CH2, that group is repeated many times. There is, so the structure that he has drawn, that means this. So for example, there is C12H25. So there are 12 carbons here and 25 hydrogens here, and then there is one oxygen, and there is an arrow like this and like this, and this portion is repeated n times, where n is typically 3. Okay. And
Yeah.
then this is combined to OSO3Na. Okay. So this is a detergent. So what this structure means, so we'll get into details of how to understand these structures. But each point here is a carbon. Okay. This is a carbon, this is a carbon. Okay. And carbon generally forms 4 bonds, right? 4
Yeah.
covalent bonds. So if you look at this particular carbon, it has 1 bond to oxygen and 1 bond to another carbon, right? So
Yeah.
2 other bonds are missing. They have not specified what, right?
Yeah.
So what is assumed here, whenever you draw a structure like this, it means that 2 others are hydrogen. Okay. So there are 2 hydrogens here, which will not be written down because it is annoying to keep writing hydrogens. Okay. So here also there are 2 hydrogens, right? And then this carbon is connected to another oxygen, and there is an SO3 here. So notice that this portion looks like an ionic portion. This will be Na plus and this will be SO3 minus, right?
Yeah.
So this whole thing till here, right, is the anion. Okay. And this is the cation.
Okay, got it.
And SO3 minus is there. So obviously you can draw a structure like this, SSOO. And it could be double bond and all here, like depends on what the structure is. And there's a negative charge also. So negative charge also, that means there's 1 extra electron than predicted, right?
Yeah.
So the whole structure can be drawn in detail, but what I want you to notice right now is that whenever some line is drawn like this, right, what it means is, basically that there is a C at every point, C, 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 okay, C, 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 and the hydrogens are not drawn. So if you look at this C, it has to have 3 hydrogens, right?
Yeah.
And this C has to have 2 hydrogens because it is connected to 2 other carbons, right?
Yes.
And this has 2 hydrogens, and this has 2 hydrogens, and so on, right? And last one has 3. So the actual molecule will be more complicated and the formula will be bigger. You are not specifying the hydrogens. Okay. So in this table, again, he talks about different molecules. Right now, you will not understand much here, but you just notice the shapes and the types of molecules that can be formed. So see, sometimes there are rings here, right? So for example, for that Melaleuca, that is a leaf oil that has a nice ring, right? Terpenen for all, right? So the problem here for organic chemists, the problem is really serious because there are so many compounds, first of all. And if you want to talk about science and all, you will have to come up with a way to name them, right? Otherwise, you will not know what the other person is referring to, right?
Yes.
So you will have to name the compounds, and you will have to name them in such a way that it makes sense to a third person also. So now there is a whole chapter that you will study, which will be on nomenclature. So you will study the rules of how to name organic compounds. Okay. Because there is some convention that has to be followed. Only then will people be able to understand what the other person means, right?
Yeah.
You cannot give arbitrary names. Okay. So for earlier people, when they started studying, they gave arbitrary names like benzene. Benzene doesn't have an C6H6, everyone knows. But benzene doesn't give us any indication that it will be C6H6. Right?
Yeah.
This is called a common name. So many common names were used. Acetone. Acetone is CH3COCH3. But it doesn't give us any indication of the structure. It is just a common name, right?
Yeah.
So there will be a proper way to name this so that even if someone did not see that compound before, they will be able to deduce the structure from the name of the compound, right? So that nomenclature is done by the International Union of Pure and Applied Chemistry, IUPAC. And IUPAC naming convention is followed for writing the names of these and other chemical compounds, right? So we will see that as well. That is important because one question will be there, one or two questions could come in organic, which is just about figuring out the name of a particular structure. So you can read this. This is just interesting stuff, this whole portion. It is not very difficult or anything. It's just descriptive. So there's nothing much to remember here also. Organic chemistry and the periodic table, all the compounds we have shown you are built upon hydrocarbon skeletons. So that is what we mean by hydrocarbon skeleton. So this is the skeleton on which they were built, right? You could have some O, something else attached, right? But ultimately the skeleton is C and H, right? So that is called the hydrocarbon skeleton. It is carbon and hydrogen that make up the bulk of the organic compounds that you see. Okay. So, however, you could also have some other elements, mostly oxygen, nitrogen, sometimes there is sulfur, phosphorus, and sometimes there are halogens, which is fluorine, chlorine, bromine, and iodine, right? So
Yeah.
these are the major elements that you will encounter throughout this textbook. And it is remarkable that with just so few elements, you are able to make so many compounds, and there is such a wide variety of chemistry that is possible with just this much, right? So,
Yeah.
so ultimately, like if there are only like carbon, if there is only carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and some halogens, so how how is so much being possible? How is there a textbook which is 1,000 pages plus for just these many elements, right? So you understand, because inorganic chemistry on the other hand has how many elements? There are so many elements, right?
Yeah, and it has like very
Like,
less number of
so
compounds.
there is S block, P block, so many other elements. However, that is slightly lesser number of reactions you will encounter there than you will see here. So the thing that is remarkable is that carbon and hydrogen and these together can combine in so many different ways to create so many different compounds, and they can build long chains, right?
Yeah.
So they can make long chain compounds, which even though the number of elements is small, but the compound is quite complicated, right?
Yeah.
This long chain compound that is formed through carbon is not a property that is shared by many other elements. So, for example, silicon forms some chains, but not too many elements can form chains like carbon. Okay, chains or rings. Also, this tells us that if there is such a wide variety of chemical compounds which are organic compounds, then there must be something about the structure. So what we will learn throughout the book is that structure will always influence reactivity. So it is
Okay.
about the way the organic compounds are structured, that is what is influencing their reactivity. And the structure of organic compound, if you know, then based on the structure and some more knowledge, you will be able to predict what is going to happen. So so the last paragraph of this chapter is very important. It says this book is about all these things. It is about the structures of organic molecules and the reasons behind those structures. It is about the shapes of these molecules and how the shape relates to their function, especially in the context of biology. So it explains how these structures and shapes are discovered. It tells you about the reactions the molecules undergo, and more importantly, how and why they behave in the way they do. You understand, right?
Yeah.
So this is the landscape that we are going to learn. It is quite difficult sometimes because there's a lot to learn here, but we will see. Uh, Chapter 2 is organic structure. So now we'll start looking at some of the structures and trying to understand how to name them. Okay. So see what he's saying. There are over 100 elements in the periodic table. Many molecules contain well over 100 atoms. Well over 100 atoms. For example, he is giving an example of a anti-cancer molecule, palitroxin, which has 129 carbon atoms, 221 hydrogen atoms, 54 oxygen atoms, and 3 nitrogen atoms. So he has given the structure also here for the palitroxin molecule. So it is occupying almost the whole page, right?
Yeah.
So it is easy to see how. So now, right now, if anybody tried to give a proper name for this palitroxin, right, it would be really hard for him to name it, right? You understand? The
Yes.
name itself will be super long.
Yes.
You will have to specify which carbon has the oxygen bond. See, there is on top on the right side, there is a OO bond, right?
Yes.
Which carbon has N attached to it? NH, there are many NH attached to it. No, actually, there are 3 nitrogens attached, right? So you will have to specify which carbon has the NH attached to it, because if you put the NH somewhere else, no, it's a different molecule. So that is something called isomerism. Isomerism is a important concept where if I have the formula, like here in case of this compound, the formula would be something like this. Palitroxin would have a formula like this: C129 H221 O54 N3, right?
Yeah.
Something like this. But this formula doesn't tell us anything about the structure, no?
Sure. Yeah.
Right now, I don't know how it will look, right? However, the big structure that is explained there, right, that is drawn there, that literally tells you how everything is connected, right?
Yeah.
So the problem, however, is that you can have the same formula and you can have a completely different looking structure, right?
Yes.
Completely different. I can arrange it in any way. I can just follow some basic rules, like carbon should have 4 bonds and all, and oxygen, everyone's octet should be complete, right?
Yeah, and then you can arrange it whatever way.
You can have a completely different structure, and as predicted, the structure will influence reactivity. This will be a completely different molecule also, and it will have totally different properties. Okay, so you cannot completely different compound it will be, right?
Yeah.
So the problem now becomes that for each structure, you will have to name it uniquely, right? You should not have like same name and different structures, right? So isomerism basically says that the chemical formula will be the same, but there will be many different structures possible for those organic compounds, and these will be separate organic compounds. Such organic compounds which share the same chemical formula but have different structures are known as isomers. Okay, so in this case, we will not try to draw any isomers. We can draw isomers very easily, however, for other compounds. So for example, CH2, CCl2, right?
Yeah.
Suppose this is my compound. Now I can draw this structure, right? This is one structure. However, I could also have drawn this structure like this, right? Do you notice that they are different?
Yes.
So in one of them, one carbon has the 2 chlorines. In the other one, the chlorines are separate, right?
Yeah.
There could also be a structure which is different in this way. So actually, this and this are also different. It's not about which one is connected. It's also about how they are connected, right? Here, chlorine and chlorine are opposite ends to each other, right? And hydrogen are opposite ends, right? So
Yeah.
this is called the trans isomer. And this is called the cis isomer. Cis means same side. Cis isomer. Because chlorine are on the same side here, right? And here chlorine are opposite sides.
Yeah.
This is a completely different structure, right? So actually 3 different molecules we have already drawn, 3 different compounds these are, okay? Their properties will be different, okay? So this is just a simple example for how it could be complicated, right? A simple molecule with this formula can be written in so many different ways, right?
Yeah.
We will see more such cases and we'll learn how to differentiate between them. So now, okay. So, but how can we understand what seems like a recipe for confusion? Faced with the collection of atoms we call the molecule, how can we make sense of what we see? This chapter will teach us how to interpret organic structures, okay, and also how to draw organic molecules in a way that conveys all the necessary information and none of the superfluous information. So let's see. Organic chemistry is the study of compounds that contain carbon. All of them contain also hydrogen. Most also contain oxygen, nitrogen, and other elements. So some molecular structures are shown below. These molecules are all amino acids. Amino acids are the constituents of proteins. So look at them and notice what is common across all of them. So glycine, alanine, and phenylalanine. So what will you see is common across all the three molecules, right? There is one thing that is definitely common. There is COOH in everyone, right?
Yes.
Can you see the COOH thing?
Yeah.
There is COOH in everyone and there is NH2 also in everyone, right?
Yes.
So almost like this portion is there in everyone. NH2,
C.
C, and O and OH, right?
H. Yeah.
So this portion is common to everyone. This portion is called a, so after that things could be different, right? After that things could be different. This portion is called an carboxylic acid group. Carboxylic acid group. And this C to NH2 link, this portion is called an amine. Okay. So what is happening actually is that this is an acid plus an amine, right?
Yeah.
So COOH group, whenever you see a COOH group, think of it as a carboxylic acid. So basically what we are learning right now is ways to recognize some patterns, right? So this is a carboxylic acid group and CnH2 is a amine group, right? And
Yeah.
the combination, when you see both together in a molecule, you will say that that is an amino acid, right? Amino acid, correct?
Yeah.
So see that all three have that, right? So what we will first focus on, and that is how many of the chapters of this book will be structured around, where we will learn about certain particular functional groups, okay? So what is a functional group? Let's understand the meaning of the word. Functional group is basically a collection of atoms that behaves in a similar way. A collection of atoms that have specific properties, that have specific chemical properties. So in the sense that no matter where you see a COOH group, right, it will have a certain behavior that it will want to lose the H plus, right?
Yes.
So even if the compound is super complicated, like phenylalanine, look at that. It's much more complicated, right?
Yeah.
But phenylalanine and glycine, both of them will want to lose their H plus to some degree, right?
Yeah.
When they are in a particular medium, they will have that property of being acidic, right?
Yeah.
So you can now basically say that both these molecules share that particular functional group. So they must share some particular chemical properties of that functional group, right?
Yeah.
So if you can learn and understand different functional groups and how each functional group is supposed to react, then you will be able to look at a molecule and predict what that molecule is likely to do, right?
Yes.
Correct. So
Yeah.
instead of a disorganized, unorganized study of chemical organic compounds, what we will be studying is we'll be grouping our organic compounds under functional groups. Okay. And we will study each functional group separately and try to understand what the properties of a particular group will be. Right. And once we know enough chemistry of each functional group and we are able to understand how those functional groups will react in different situations, we will be able to basically talk about reactions of many different compounds, right?
Yeah.
So the functional groups that you will encounter in the book are basically, many are there, So there is an alcohol group. This is an alcohol when C is connected to an OH. Alcohol, for example. There is, just now you saw COOH, right? This is a carboxylic acid, right?
Yeah.
Then there are many such other ones also. This is an aldehyde. C, CHO. This group is an aldehyde. Okay. This can be connected to other things here, right?
Yeah.
And this is an aldehyde. Then there will be a ketone group. Then there's a ketone group where CO is there, and then C can be connected to other things. Whenever I say this part is connected to other thing, it can be complicated here, right?
Yeah.
This part can be anything. Whenever you notice this much only though, right? That is an alcohol. Here O and H have single bond. Here O and H have single bond, but C has a double bond, right? CO. So this is the common portion that is the functional group. Everything else can be different. It could have multiple functional groups also, right? Like for example, we saw the amino acids have an NH2 also and a COOH also, right?
Yeah.
This is the aldehyde group. This is the ketone group. So here there are two lines here. So that means this part and this part could be anything, right?
Yeah.
This is a double bond. This is an alkene. If it's a single bond, it's a simple hydrocarbon.
Yeah.
That is an alkane. Alkane. There could also be a triple bond sometimes. That is an alkyne. Okay. Then there are other things also. There is amines. Amines are CnH2, right?
Yeah.
This is an amine we just now saw. NH2 thing was there. There are amines. There are carboxylic acid, aldehydes, ketones, esters. Esters. There are more actually. Ethers. The benzene group. Benzene is a ring structure like this. Aromatic compounds. So we will see. Right now, you don't have to remember all of this. I'm just listing down some different chapters that will. So this will be a separate chapter, for example. So we will be studying only the alcohol group and how organic compounds which contain this group will react, right? So that is the way in which the whole subject will be dealt with. Obviously, there will be some exceptions. Not all the chapters will be about a particular group. It could also be about a particular reaction. So let's go ahead in the book. See, he's saying lysine has a chain of atoms, whereas tryptophan has rings. So see, tryptophan has a carbon ring and then there's another side ring also, right? However,
Yeah.
what is common between both of them? Both of them have that amino acid group, right?
Acid group. Yeah.
Right. So yet all of these, so many different structures are there, yet all of these molecules have similar properties. How? They are all soluble in water. They are all both acidic and basic, basically amphoteric, right? They can all be joined with other amino acids to form proteins. This is because the chemistry of organic compounds depends much less on the number or arrangement of carbon or hydrogen atoms than on the other type of atoms in the molecule. So basically, the most of the chemistry is going to be determined by the other special atoms that are attached, right? And very less on the way the structure is or how long it is and how many hydrogens are there and stuff. That is not going to be the main determining factor. Okay. So we call parts of molecules containing small collection of these other atoms as functional groups simply because they are groups of atoms that determine the way the molecule works, right? All amino acids contain two functional groups, an amino or NH2 or NH group and a carboxylic acid COOH group. Some contain other functional groups as well, right? So now he's talking about how the functional groups determine the way the molecule works both chemically and biologically. So obviously in our body, the organic chemistry is much more complicated, where the molecules are more complicated and structure again determines reactivity to a large extent. So it's almost so complex that sometimes one particular isomer or one particular compound is going to have one property and its exact mirror image, right, will have the opposite properties also. It could be. So you will see some isomers which are called stereoisomers. Stereoisomers are such that there is a compound here, let's say CClH O, or okay, I want to get an example of a simple stereoisomer. So you could have CX, Y, Z, W. X, Y, Z, W or anything. Okay, they are just different from each other. Okay. Now this figure is not an accurate representation because this figure is supposed to be 3D. Okay, this figure is supposed to be 3D. So you will have a tetrahedral structure where carbon is at the center of the tetrahedron. Okay. And some two lines here will be in the plane, and one line will be going into the plane, and one line will be coming out of the plane. Okay. And carbon will be the center of the tetrahedron. Now, in this structure, it is possible to have stereoisomers in the sense that just the way your right hand glove cannot fit into your left hand glove, right?
Yeah.
Your right hand will not fit into the left hand glove, right?
Yes.
In a similar way, if you take the mirror image of this, right, you will get a structure which looks like this, right? Correct?
Yes.
It has a different orientation. Okay, so it is, think of this as a right-handed structure, and this is the left-handed corresponding structure. Okay, left-handed structure. So we will learn rules of how to understand this. For now, just imagine this CXYZW is in space. Okay, so C is in the middle of a tetrahedron. A tetrahedron is a structure that looks like a pyramid, right?
Yes.
It is like this. There's a thing on top, and then there are this type of situation, right? And this is one X, let's say, and this is one Y, and this is one Z, and this is one W, right?
Yes.
And in the center there is a carbon, right?
Carbon. Yeah.
So you can say that X and W are in the plane, Z is coming out of the plane, and Y is coming into the plane, right? I mean, it is hard to draw and show you, but
Yeah, I got it.
right. So this is one possible structure, right? However, if you do this, in this structure, it could be X and Z are in the plane, and Y and W are doing that into and out thing, right?
Yeah.
Basically, it's a different orientation, and the difference in the orientation is such that it's a mirror image of each other. Okay, mirror image about some plane. Okay, so what we will see is that this molecule has completely different properties than this molecule. Okay, which is remarkable because almost everything is same here.
Yeah.
It is just the way that a right hand glove, if you reflect, you will get a left hand glove's image in the mirror, right?
Yeah.
Similarly, here also it is reflected, and just like you cannot fit your right hand in the left handed glove, similarly the reactions of left-handed counterpart will not be the same as the right-handed counterpart. Because in the actual cells of our body, the reactions are dependent on how a particular molecule fits into a certain enzyme, or how it fits into that enzyme and reacts. If it is unable to fit because it is of a different reflection or different handedness, right, then that enzyme will stop working. You understand?
Yeah,
Only a particular type of molecule will be able to fit perfectly and do the reaction. Okay, so you will see cases where one isomer is going to have some beneficial effect and the other isomer is going to be bad for us. So it is so complicated in the real life organic chemistry that is going on in your biological systems. It is really complicated. So we will see examples of that. For now, let's just go on here. He's saying that isn't to say that carbon atoms aren't important. They just play quite a different role from those of the oxygen, nitrogen, and other atoms that they are attached to. Okay, so we can consider the chains and rings of carbon atoms we find in molecules as their skeletons which support the functional groups and allow them to take part in chemical interactions, right?
Yeah.
Much as your skeleton supports your internal organs so that they can interact with one another and work properly. Okay. We will see later how the interpretation of organic structures as hydrocarbon frameworks supporting functional groups helps us to understand and rationalize the reactions of organic molecules. Basically, if you think of it in this way, then you will be able to boil down the millions of reactions into certain major classes. Like each functional group can only do certain few classes of reactions. And similarly, because you have 10, 15 functional groups, if you learn those 30, 40 different classes of reactions and how each of them behaves, then more or less you cover so many different types of reactions, right?
Yeah.
So this section is the next section, which will teach you ways to draw and write molecules, is extremely important because it will teach you how to communicate chemistry clearly and simply throughout your life as a chemist. Okay. So drawing molecules, be realistic. So you don't have to draw the entire structure like this, right? So this is linoleic acid, right? So what we want to avoid is writing all these CH2, CH2, right? So see, he
Yeah.
has drawn this CH2, this structure in multiple ways. First, he has marked everything. Then he has noticed that the third figure is a straight line representation, right?
Yes.
And in the first figure, there is a curvature to the actual carbon-carbon atoms, right?
Yeah.
So that is more realistic than this. Carbon atoms are not going to be in a single straight line, okay? They are going to be arranged in this zigzag, zigzag manner, right? Now
Yeah.
how do you explain or how do you write that structure? What we will eventually do is remove all the H and the C from the zigzags, okay? And wherever there is a difference, the difference is in, first of all, in the double bond C, double bond C part, right?
Yeah.
And also there is a difference when you come to the COOH at the end, right?
Yes.
So notice on the next page, finally when he draws it, right? He draws just lines for the carbons, removes all the hydrogens, every double bond he's marking, right?
Yeah.
And at the end, he has attached a C double bond OH, right?
Yeah.
He is not even showing the C at the end, he's just showing double bond OH, right? So that is the way
Yes.
you represent this linoleic acid, right? So what is important here to know is that the first C, first C at the beginning of the chain will have 3 hydrogens, and every other C will have 2 hydrogens except at those points where it is different, right? There is a double bond at one place between the 1, 2, 3, 4, 5, sixth and the seventh carbon, right?
Yeah.
Between the sixth and the seventh carbon, there is a double bond, right?
Yes.
So notice how many hydrogens will be at the sixth carbon and the seventh carbon.
There'll
Tell
be
me how many hydrogens should be on the sixth and the seventh carbon.
one each.
One each on the sixth and the seventh carbon. Similarly, eighth carbon will have two, but ninth and 10th carbons will have one each.
One each.
Similarly, everyone else will have two, two, two till the end, and the last carbon will not have any hydrogens, right?
Yeah.
Because it's already making 4 bonds. One double bond with oxygen, and then 2 other bonds with one with carbon and one with oxygen, right?
Yeah.
So this is the way you represent it finally. So you should read the whole part, be economical and stuff. He's talking about how to draw this, right?
Yeah.
And every kink in the chain represents a carbon atom. End of the line represents a carbon atom. And he has already said, we have already discussed those parts. So next, let's go on to the next page. Now he's going to show some different structures of the same compound. So leucine he's seeing, and he's saying it doesn't matter which way up you have drawn it, but your diagram should look something like these structures. See, the first and second, the only difference is that NH2 was on up or down, right?
Yeah.
That doesn't matter. That doesn't matter right now, at least, right? Because it is not known right now which way up is and where NH2 will be, right? You have to determine that experimentally what is the orientation of NH2 and all, right? So this structure is identical. Similarly, you can write it in a reverse manner and start from COOH this side, right? That is also fine. You can basically rotate the structure anyway, it doesn't matter, right? You could draw any of these four and it's still fine, right?
Yeah, get it.
Okay. Then, okay, now turn back to page 16. Try redrawing some of the other 8 structures there using the guidelines. Don't look at our suggestions below until you have done them. Then compare your drawings with our suggestions. Okay, so page 16 had some 8 compounds, right? So other than leucine, there were many others also, right? Yeah.
Yeah.
And he's asking you to just draw the uh, dot and dash structure, right? The the zigzag arrow, zigzag structure, right? Line structure that is called, correct?
Yeah.
So he
Yeah.
has drawn those for you, and you should check yourself whether you are able to draw it or not. These are called structural diagrams. Now, on the next page, he's talking about how structural diagrams can be modified to suit the occasion. So he's saying you'll probably find that you want to draw the same molecule in different ways on different occasions to emphasize different points. Okay. So let's carry on using leucine as an example. We mentioned before that an amino acid can act as an acid or as a base, right?
Yeah.
So when it acts as an acid, a base removes H plus from the carboxylic acid group, right? So if amino acid is acting like an acid, what will happen is that it will give up its H plus, right, to some other basic thing, right?
Yes.
So let's say you added an NaOH thing outside to the solution. So what will happen is OH minus will come from NaOH and they will want to take the H plus from the leucine acid part, right?
Yeah.
Leucine had that carboxylic acid COOH and that H will be lost, right? So the structure will become, leucine will have a O minus, no?
Yes.
Because H plus has been lost, no?
Yeah.
So what is happening here is, look, the OH bond has been drawn clearly here with a single line between them, which represents a single bond, right?
Yeah.
And if you want to lose H plus from this, so what is H plus? H plus is actually just a proton, right?
Yes.
So if the proton comes out here, then the hydrogen has given up its electron, no? Right?
Yeah.
So right now, when the OH bond was there, the single bond there has 2 electrons that are equally shared, right?
Yes.
One of them came from O, one of them came from H, right?
Yeah.
However, if the H plus goes out without taking its electron, then that means the single bond's electrons are completely going to belong to the O now, right?
Yes.
Therefore, that arrow, curved arrow has been drawn, which says that that bond, entire bonds, both the electrons are going on the oxygen now, right?
Yeah.
Correct. So oxygen normally should not have that excess electron, no, one excess electron that is going to come now, right?
Yes.
Correct.
Yeah.
Normally it would have been neutral, right? When it had formed its 2 bonds, right? But now it gets an excess electron from this single bond that was broken, right?
Yes.
So it becomes a O minus. Basically, there will be a lone pair of electrons on the oxygen now, right?
Yes.
And the H plus goes out and combines with O minus to becomes H2O, right?
Yeah.
So the product of this reaction has a negative charge on an oxygen atom. We have put it in a circle to make it clearer, and we suggest you do the same when you draw charges plus and minus. Plus and minus signs are easily mislaid. We shall discuss this type of reaction, the way in which the reactions are drawn, and what the curly arrows on the diagram mean in chapter 5. But it means that only that the double bond, the single bonds electrons moved from being equally shared to going completely to the oxygen,
Oxygen.
right?
Yeah.
That's why it became negatively charged. But for now, notice that we drew out the CO2H fragment on the left. We drew out the COOH, right? Earlier, we were writing simply COOH, right? In some structures. Look at the leucine on the other page. We are just writing COOH, right?
Yeah.
But here, he drew it out properly by writing C double bond O and then OH single bond, right?
Yes.
Because he wanted to focus on the OH minus that was attacking it, right?
Yeah.
If you draw it out separately, then here you will realize what happens when a proton leaves, right? But if you had just written COOH, then it might not have been clear what will happen when OH minus will react, right?
Yeah.
Okay, so we have modified our diagram to suit our purpose here. Similarly, it can also act as a base. It will act as a base when that NH2 group will react. Okay, so that amine group, right? So NH2 right now has a single lone pair of electrons on the nitrogen, right?
Right.
If you remember NH3 structure in covalent bonding, it has a lone pair on nitrogen, no?
Yes.
So NH3 structure will be similar to this. The only difference is that one H has been replaced by this whole chain, right?
Yeah.
So N still has a lone pair of electrons. And now if water is present in the system or hydronium ion is present in the system, H plus, right? So hydronium has a plus, so it will attract the lone pair of electrons, right?
Yes.
So the lone pair of electrons can be donated to the
And
one H from the hydronium, right?
yeah.
H3O plus can give off one H plus, and then H plus can take these two electrons that are lone pair and form a complete bond, right?
Yes.
Are you understanding why
Yeah. It
two
forms a
electrons
quadrant
are forming a
covalent
single
bond.
bond?
Got it.
Yeah. So two electrons are forming a single bond, and notice why there is a plus sign now finally, right? It becomes NH3 and finally plus sign, right?
Yeah.
Because earlier it was neutral plus H3O plus, right?
Yeah.
So finally also it should have a plus charge, right? Because charge cannot be destroyed.
Yes.
Because H3O plus was deficient in electrons while the amine was neutral electrically. So finally, if it combined with the H plus, then it will have a plus charge, right?
Right.
And you can also understand it in the way that the nitrogen, which had two electrons, gave away both of them to form a double bond with proton, right? To form a single bond with the proton, right? In normal circumstances, nitrogen would have shared one electron and all, right? And formed a single bond, right?
Yeah.
Right now, it is giving away both of them. It got a plus charge, right?
Yes.
So in this portion, in this reaction, it was important to focus on the nitrogen part, which was behaving like an electron pair donor, right? Electron pair donor is a Lewis base by definition,
Right.
correct? So the same compound can be exhibiting different types of behavior depending on each functional group's behavior, right? So that is what we are learning here. Now, what he will say is that the structural diagram can show three-dimensional information on a two-dimensional page. So that is what I was talking about earlier when I was talking about that tetrahedral structure, right? Of C, X, Y, Z, right?
Yeah.
So how do we do that? So he's saying, of course, all the structures we have been drawing give only an idea of the real structure of the molecule. For example, the carbon atom between the NH2 group and the COOH group of leucine has a tetrahedral arrangement of atoms around it, a fact that which we have so far completely ignored. So what is he saying here is this. Uh, so this is the leucine structure, and this is the C here, and this is the H, this is the NH2, and this is the COOH, right?
Yeah.
Now think of this carbon atom, okay? This carbon atom has four bonds.
Yes.
So this carbon atom has four charged clouds around it. So according to what we learned in chapter 7 of McMurray-Fair, right? This is sp3 hybridization
Yeah.
and tetrahedral structure, right?
Yes.
Tetrahedral structure. So technically, we can do the same thing for each of the carbon atoms and realize that it is a chain of different tetrahedrons which are linked together, right?
Yes.
So the arrangement is going to be a 3D arrangement. So forget about for now the remaining part, but notice that this part is one portion that attaches, H is one portion that attaches, NH2 is one portion, and COOH is another portion, right?
Yeah.
So the way the whole structure is going to be a tetrahedron in space. Just hold on for a moment. I'm getting a call. Hello? Yeah.
Yeah.
So again, what we want to, we cannot represent a tetrahedron as a plane figure, okay? And in a two-dimensional screen, it is very likely that we are doing just that so far, right? So
Yeah.
actually, to draw the structure properly, we make use of this convention that uh, everything that is a normal line, right? A normal shape of line, a normal looking line is in the plane of the paper. Okay.
Okay.
In the plane of the paper, everything that is a darkened line like this is coming out of the plane of the paper,
All right.
and everything that is a dashed line like this is going into the plane. Okay.
Okay.
So see the second and the third structures that he has drawn, right? Correct. Second structure that he has drawn at least, right?
Yeah.
So in the second structure, he has connected one hydrogen with a dashed line, right?
Yeah.
And the NH2 with a darkened line, correct?
Correct.
And the normal other parts are connected by normal single lines.
Lines. Yeah.
So those single lines are in the plane. One NH2 is coming out of the screen and one H plus is going into the screen, right?
Yeah.
So now it gives the type of feeling of a tetrahedral structure, which is going to be 3D in nature, right?
Yes.
So what he is saying is, we want to emphasize this fact by drawing in the hydrogen atom we missed out at this point. We can then show that one of the groups comes towards it out of the plane of the paper, and another group goes away from the plane, away into the plane of the paper, right? There are several ways of doing this. In structure 2, the bold wedged bond suggests a perspective view of a bond coming towards you, while hashed bond suggests a bond fading away from you, right? The other two normal bonds are in the plane of the paper, correct?
Yeah.
Alternatively, we could miss out the hydrogen atom and draw something a bit neater, although slightly less realistic, as in structure 3. He's right now not showing that hydrogen that is going into,
Yeah.
right? Okay, where we can assume the missing hydrogen atom is behind the plane of the paper, because there that is where the missing vertex of the tetrahedron attached to the carbon atom lies, right? When you draw diagrams like these to indicate the 3D shape of the molecule, try to keep the hydrocarbon framework in the plane of the paper and allow the functional groups and other branches to project forwards or backwards, right?
Got it.
So these conventions allow us to give an idea of the 3D shape of any organic molecule. Now he will ask you to draw some examples and all. And after this, now we'll start doing the hydrocarbon framework. So how to think about the long chains that we have been seeing so far, right? So the simplest kind of hydrocarbon framework that he will talk about is these normal alkane chains, right? So from this point onwards, there are some names and all that you will need to know. This point onwards, we will continue in the next class. But what I want you to do is read chapter 2 entirely anyway. Okay.
Okay.
Chapter 2, definitely read through and start chapter 4 also, because next class we'll be discussing mostly chapter 4. Okay.
Okay.
So half an hour at least we will be doing chapter 4. Chapter 2, we will do all the conventions and all, whatever is after this point, right? Chapter
Yeah.
2 and chapter 4 will be discussing. So just read through, and also the stuff that we have not yet read in the first chapter and the second chapter, right? The actual text of the book. So the
Yeah.
book is really nice, and when you start reading, it will be quite interesting. Okay. So
Okay.
except chapter 3, just go through as much as you can, chapter 1, 2, and 4. It will be quite interesting. Okay.
Okay.
Uh, the reactions will start from chapter 5 onwards. So chapter 5 is the organic reactions chapter, and after that he will start showing you small examples, and basically we'll start learning the chemistry part. Right now we are just basically preparing the ground for learning the reactions. Okay.
Okay.
Okay, tomorrow we'll do a class, we'll do maths. Okay.
But
uh, so we'll continue. We were doing what last one? We were doing functions only, properties of periodic functions and stuff, right?
yeah, you said you were going to start with limits the next class.
So limits will start tomorrow. Okay.
Okay.
Uh, Yeah, I'll see you tomorrow then.
Okay, goodbye.
Bye.
Thank you.
Mm.